Okay, let's start. So, okay, question in the chat. I'm still a little confused as to why the algorithm from the end of the last lecture works. Let's see. So the algorithm was something like you were given a sequence of AIs, AI between 0 and n minus I, and you're trying to recover a permutation W such that the major index of W is equal to the sum of the AIs. Or is that the question? It's been a week for me since the lecture was recorded, so I don't remember. Yeah, okay. All right. So yeah, I didn't quite explain this explicitly. I left it as an exercise, I guess. But is there a specific part that's causing the problem? Just like why it exists and why it is unique, so all of it. Okay, so I guess you're asking whether when I when I try to insert some element into a permutation, why is the place of insertion unique, and why does it exist? And okay, so I mean, I gave some non-rigorous explanation, but okay, let's try to prove it. So let's say you have a permutation W, W1, W2, W3, etc., Wn, and you're trying to insert, let's say these are numbers from 1 to n in some order, and I'm trying to insert 0 into W. So I'm trying to insert the number that's smaller than the rest of the numbers. Now let's see what happens if I insert it at the end. At the end, so it's going to be W1, W2 up to Wn, and then 0. So and I'm trying to figure out how much is the major index going to change. So if there is a 0 at the end, then the major index is going to change by n. By plus n. Right, because if you create a new descent at the last position, and the major index takes the sum of positions of descents, so the extra descent is going to contribute plus n. And now let's see what happens. So let me denote the descent set of W by, let's say, d of W is d1 less than d2, etc., less than dk. So these are the positions where the descents occur inside W. So what I claim is that if you insert 0 at dk, right, so W was something like there was x and y and x at position dk and y at position dk plus 1, and let's say x was bigger than y, so there is a descent, then this becomes x0 y dk plus 1 dk plus 2. So the new descents are x is bigger than 0, and that's it. Right, so y is not bigger than anything, and since dk is the last position of descent, there's no more descents to the right of my insertion. Right. So in particular, and the descents which are to the left are unchanged. So the claim is that in this case the major index changes by plus 0. Yeah. For those of you who have just joined, I'm trying to explain rigorously the bijection from the last lecture. In particular, why can I insert 0 into a word which contains integers between 1 and n in such a way that the major index changes by any value that is given to me beforehand, and each value occurs exactly once. So what I claim is that if I insert 0 at dk minus 1, then the major index changes by plus 1 by the same argument, right? There's if this position is dk minus 1, then there's a descent, so you create the same descent here, but there's going to be one extra descent to the right. So this extra descent is going to move to the right, one step to the right, and in particular the sum of positions of descents is going to increase by 1. So that's where you get plus 1. And similarly, if you insert 0 at dk minus 2, or it's at, let's say, dk minus I, then the major index changes by plus I for any I from 0 up to k minus 1, I think. Yeah, that's the... is that clear, or does it require more explanation? All right. So the only question is, what happens if I insert 0 at some position which is not a descent? Okay, let me do some notation. Let's say maybe n without descents of w is ascents. So let's say this is a1 less than a2, etc., less than a n minus k minus 1 probably. Or, well, okay, so well, let's say a n minus k. Right? So in particular, a n minus k is equal to n, because the set of descents is a subset of bracket n minus 1. So this is the last position where you insert at the end, and then these are all other positions where you have an ascent. So if I insert, as I said previously, insert 0 at the end, so to the right of a n minus k, which is equal to n, then the major index changes by plus n. And now what happens if I insert at a n minus k minus 1? So again, w is blah blah blah, x, y, blah blah blah, where x is in position a n minus k minus 1. So and there is no descent, so x is less than y. Now I transform this into blah blah blah, x, 0, y, blah blah blah. And so I create a descent. Right? There's a descent between x and 0, and there is no descent between 0 and y, and all because a n minus k minus 1 is the rightmost ascent, right? Then I get that all so there is no all these elements to the right, they form descents. So in particular, there is the number of descents to the right is exactly, I think, something like n minus a n minus k minus 1, something like this, minus 1 probably, whatever. And so you move all of these, right? Because by definition, this is the rightmost descent, rightmost ascent of your permutation. So and x is in position a n minus k minus 1. So I create a new descent, and therefore my maj changes by a n minus k minus 1 plus, because that's the new descent, plus I also move all these other descents one step to the right. How many of them are there? Plus n minus a, n minus k minus 1, minus 1. And this number is equal to n minus 1. So, and you can, so the idea is that by induction, if you insert 0 at a n minus k minus j, then the major index is going to change by n minus j for j from 0 to n minus k plus a minus k minus 1, whatever. So that's the, I don't know if that's more rigorous than what I said in the last lecture, but that's as rigorous as I can get. Is it satisfactory, or it should explain more? Yes, that makes sense. Thank you. Okay, thanks. All right, let's start the lecture. Welcome back from the midterm. And I hope I'd like to start with a problem. So here's a recreational problem, which may or may not have anything to do with what I'm gonna discuss or what I've been discussing so far. So here's a problem. It's called the 100 prisoners problem. And here's a picture from Wikipedia, which somehow represents the problem, I guess. So what do we have? We have 100 prisoners, and 100 prisoners which are numbered, and 100 drawers which and each drawer contains a number from 1 to 100 in random order. Right, so each number appears exactly once, but they are permuted randomly inside these 100 drawers. And the conditions are that each prisoner opens exactly 50 drawers, one by one or simultaneously, doesn't matter. Well, I mean, it's up to them. And the conditions are if everyone opens a drawer with their number, then they all win. Whatever win means for this game. Maybe they get released from prison, and otherwise everyone dies. So so yeah, you imagine you're a prisoner and you have 100 drawers and you're trying to guess to open 50 of them and find your own number. So the question is, how do you do that? If you are allowed, can discuss the strategy beforehand, but no communication is allowed after the game starts. And the question is, well, what is the optimal strategy, and what is the what success probability does it give? Some of you probably know this problem. It is on Wikipedia, but if you don't know, then I suggest you think about it. And I'm not going to tell you the answer, maybe until, let's say, the next lecture. But what I can tell you one strategy. One strategy, which I'm going to call the dumb strategy, is if you can open 50 random drawers, and the probability that you're not gonna all die is 1/2 to the 100, which happens to be a very small number, right? So as you know, 2 to the 10 is bigger than 10 to the third, so this is less than 10 to the 30, 10 to the negative 30, so that's very small. So the question is, can you do better? If you can, provide a strategy. If you cannot, then prove that this strategy is optimal. That's it. That's the problem. And I'm going to discuss this later. Any questions on the problem? All right. Yeah, they don't know that. Any other questions? All right. Yeah. So, okay, now let me go back to permutations and inversions and all that. Do they have to open their 50 drawers consecutively? Well, they can do whatever. They can do consecutive. They can even consecutively, meaning each prisoner enters the room, opens 50 drawers any way they want, and then leaves the room. And then the next one comes, and they. Okay. So, are you going to explain the dump star? Yeah, I'm not sure if that's a joke, but anyway, I'm not familiar. The dump strategy. Explain. Well, so the explanation is the you open 50 random drawers. So the probability that you find a drawer with your number is 1/2. And because everyone has to find their own number, that means that the total probability is you multiply all these independent probabilities, and you get 1/2 to the 100. That's the explanation. Is that the answer to the question, or am I missing something? Probability of finding your number is 1/100. Well, if you open just one drawer, then it's 1/100. But if you open 50 drawers, well, you can do this consecutively or simultaneously. It doesn't matter, because you open exactly half of all the drawers. If your number belongs to that set of 50 drawers, then you win. Okay, thanks. Yeah, so, all right, inversions. So remember, we were discussing inversions, and if you have a permutation W in Sn, then the inversions of W are just pairs 1 less than I less than J less than N, such that Wi is bigger than Wj. So today I'm going to discuss, first of all, I'm going to try to explain even and odd permutations, which you may have seen in your linear algebra class. W in Sn is even if the number of inversions of W is even. And otherwise, it's called odd if the number of inversions of W is odd. Okay. For example, let's try to count how many odd and even permutations are there. The size of Sn is n factorial, and I claim that lemma the size, so the number of odd permutations in the Sn is equal to the number of even permutations and is equal to n factorial over 2 for any n greater than or equal to 2. And why is that? Can somebody tell me the proof of this result? Just switch 1 and 2 and get a bijection. Thank you. Yeah, that's correct. Swap 1 and 2. You get a bijection. Or you swap the first and the second entry. Either way, you change the number of inversions by exactly 1 between odd and even permutations. Okay. Now, since I mentioned linear algebra, let me try to relate this to matrices. So for any permutation, if W is a permutation, then I'm gonna associate it. This has to do with AN in group theory, right? Yes, AN is the group of even permutations, the fact that they form a group is, I'm gonna prove it in a second, but they form a subgroup of permutations. But yeah, that is correct. So W is a permutation, then you can define the permutation matrix denoted A sub W, which by definition Aij, if the entries are denoted by Aij, then the ijth entry is equal to either 1 if Wi is equal to j, and 0 otherwise, which maybe I should try an example. Let's say let's say W is 3, 1, 4, 6, 2, 5. Then AW is going to be a 6 by 6 permutation. A 6 by 6 matrix, sorry. And okay, so W in 2-line notation, it sends 1 to 3, 2 to 1, 3 to 4. So Aij is equal to 1 if Wi is equal to j. W1 is equal to 3, so I put A1 in the first row and the third column. Let me label the rows and the columns. And 2 goes to 1, so I'm supposed to put a 1 in the second row in the first column, and etc. 3 goes to 4, 4 goes to 6, 5 goes to 2, and 6 goes to 5. Permutation matrix. Yes, this is called permutation matrix. So you have exactly in each row, you have in each row you have exactly 1, 1, and in each column you have exactly 1, 1. So these are like rooks, chess rooks, which don't attack each other. Yeah. And in particular, let's see if we can find the determinant of the permutation matrix. If you remember your linear algebra class, what is the determinant of, let's say, this matrix here, or in our arbitrary permutation matrix in terms of W? -1 to the number of inversions. Yeah, that's correct. Thank you. -1 to the number of inversions of W. And the reason is just by the definition of determinant. If you remember the definition, it is exactly you sum over all possible rook placements like this, so over all possible permutation matrices, permutations. And then you take -1 to the number of inversions times the product of the corresponding entries. And the product is going to be non-zero for exactly one permutation, which is W itself. So, okay, that's good. And, well, now I'd like to... You know that you can multiply matrices. Let me also explain how to multiply permutations so that the two correspond to each other. And that definition is actually very natural. So remember that a permutation in a sen is a bijection. Just by definition, it's a bijection from bracket n to bracket n. And if you have two permutation matrices, then you can define the product. So if you have two permutations, V and W, their product, V times W, is by definition the composition in reverse order. Oops. V composition W. And what that means, meaning is that, so this is V times W is another permutation. V times W belongs to Sn, and V W of I is by definition W of, wait, what? Well, W of V of I. Yeah, that's correct. I'm going to get confused. There's two different conventions. Either you can swap V and W, or you don't have to swap. And we're going to swap, but in many actual papers in math, people don't swap V and W. But yeah, I'm going to swap. And the reason is that this is more natural from the following explanation. Let me give you an example. I have a specific example. Well, V is equal to 4, 2, 1, 5, 6, 3. W is equal to 3, 6, 1, 5, 2, 4. So let's say I want to compute V times W. And the way I do this is I draw each of them in two-line notation. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And what I mean by V times W is that you first apply V, and then you apply W, because that's the rule for the composition. If you have a composition of functions, then you first apply V, and then you apply W to that. So in particular, if I want to first apply V, then 1, 2, 3, 4, 5, 6. What's going to happen is that one goes to 4, and 4 goes to 5. So in the product, 1 goes to 5. And 2 goes to 2, and 2 goes to 6. So 2 goes to 6. And then 3 goes to 1, and 1 goes to 3. So 3 goes to 3. 4 goes to 5, 5 goes to 2, and therefore 4 goes to 2, and etc. 5 goes to 6, 6 to 4, so 5 goes to 4, 6 goes to 3, 3 goes to 1, so 6 goes to 1. And similarly, I can multiply them in the opposite order. Let's see if I can do this. 1 goes to 4, 4 goes to 5. No, sorry, that's the opposite one. Okay, 1 goes to 3, and 3 goes to 1. So 1 goes to 1. Okay, 2 goes to 6, and 6 goes to 3. So 3, 4, 6, 2, 2, 6, 4, 4, 5. Yeah, okay. So, in particular, I'd like to draw your attention to the fact that these are different. These are different permutations. V times W is not equal to W times V. As you may be familiar, happens in the case of matrices. Is that clear, or should I explain more? Okay, I shouldn't explain more. All right, so now let me try to relate this to matrices. Lemma. If you have two permutations, V and W in Sn, then the permutation matrix of V times W is equal to the permutation matrix of V times the permutation matrix of W. And the proof is just by direct. I'm assuming you all remember how to multiply matrices, so if I multiply two matrices, AV times AW, that's the right hand side, and I take the I, k entry of this product, and by definition this is the sum over J from 1 up to n of the first matrix I, j times the second matrix J, k, and in particular this entry is going to be non-zero. This is non-zero if and only if V of I is equal to J, and this is non-zero if and only if W of J is equal to K. So in other words, I goes to J, which then goes to K. That's the only condition where I can get a non-zero product here, and in that case it's going to be equal to 1. So this is actually, well, this is 1 if VW of I is equal to K, and 0 otherwise, which by definition is so that's the definition of the matrix A sub V times W. All right, so let me talk a little bit about the algebraic meaning of this all this stuff, because I mean this is all very nice, and all these claims have names in algebra, which I'd like to briefly mention just for your general education. So you're not going to need it in the class, but so the Sn, the set of all permutations, I have defined the product, so they form a group, which the set is called the symmetric group. The symmetric group. What is a group? A group is a set with a binary operation. Set with a binary operation, which in our case is product of two permutations, and it has to satisfy certain axioms. The first one is that there should be associativity. U times V times W is equal to U times V times W, and that is true for permutations, because either way you first apply U and then V and then W. And the second axiom is that there should be the identity element, which if you multiply any element by the identity element, it stays the same. So this is the identity permutation. And finally, every element should have an inverse. So if you multiply an element by its inverse, you get the identity in either order. Inverse, which for any permutation, any permutation is a bijection. So if you take the inverse map, that's going to be the inverse with respect to this operation, this product I defined here. So that's just a quick, I'm not sure if it's clear or not, but that's a quick explanation of the word group appearing here. And in particular, if you send permutations to matrices, you send W to A sub W, that is a group homomorphism. A group homomorphism is a map which respects the products, right? It sends A times B to f of A times f of B. And yeah, so invertible matrices form a group, and I have a group homomorphism between these two groups. And even further, from invertible matrices, I can send each matrix to its determinant. Determinant of a W. The real non-zero real numbers also form a group with respect to multiplication. And because you know, since the determinant of AB is equal to the determinant of A times determinant of B, that's from linear algebra. So the claim is that the other name for this property is that determinant is a group homomorphism. So this is that's where am I going with this? I guess what I'm trying to say is that if we set -1 to the inversions of W, if we denote this by epsilon W, which is either +1 or -1, then epsilon is a group homomorphism. So epsilon V times epsilon W is equal to epsilon V times W. And in other words, if you multiply two permutations, let's say if you multiply an odd permutation by another odd permutation, you get an even permutation. If you multiply odd by even, you get odd, and etc. So if you multiply two permutations, then you know the sign of you know the parity of the resultant permutation if you know the parities of both of these, which is quite if you try to explain this from the just original definition using inversions, that's completely non-clear. Like if you multiply V and W, what's the number of inversions of V times W? That's hard, but the parity of the number of inversions has predictable nature. Let me try to finish this table. Even times odd is odd. Even times even is even. And we're going to use this knowledge a lot in the next lecture or so. Any questions so far? Or is it completely boring? Okay. No questions. All right. Now let's try to talk about cycles, which is another very nice way to think about permutations. So definition. Let's say you take a permutation, W in Sn, then you also choose, let's say you choose some number I between 1 and n. Then what I'm going to consider is I'm going to consider W squared, W cubed, etc. So I'm going to iterate my permutation as much as I want. If I iterate it many times, then each number is gonna have an orbit, right? So find the smallest r greater than or equal to 1 such that W to the r of I is equal to I. So after a while, I is going to return back to its original place, because the whole operation is invertible. and then the by definition the let me write it down like this, I, and then w of I, w squared of I, all the way up to w to the r minus 1 of I is called a cycle of w. So let me give you an example. This definition is completely weird, but I think an example would be nice. So yeah, here's an example. N is equal to 6, and w is equal to 3, 2, 1, 6, 4, 5. Or in two-line notation, 1, 2, 3, 4, 5, 6. So what I'm going to do is I'm going to, let's say I start with I equal to 1. So I draw 1, and then I look at my w. It sends 1 to 3. So 1 goes to 3. And then 3 goes back to 1. And that's one cycle. So 1, 3 is a cycle. And let me start with I equals to 2. Then 2 goes to itself. 2 goes to itself. So 2 is a cycle of w. And finally, if I start with 3, then I get the same cycle as for 1. If I start with 4, I get 4 goes to 6, 6 goes to 5, 5 goes to 4. So 4, 6, 5 is a cycle. And that's it. There's no more cycles. And so the basic properties are that the cycles are disjoint, their union is bracket n. So they give me a set partition of bracket n, but there is more information. For each cycle, I also remember the cyclic ordering of the numbers in the cycle. So yeah, each cycle is defined up to a cyclic rotation. In other words, I don't know where to start the cycle, but I know in which cyclic order they. Yeah, it's exactly the same as when you sit people at a round table. That's the same sort of equivalence relation. Yeah. So, in particular, what it's gonna be convenient, and that's a widely used notation. It's called cycle notation. I'm gonna write W is 1, 3 times 2 times 4, 6, 5. So I just write all cycles together like this. Or I can permute the cycles, or I can permute the numbers in the cycle. So this is the same as 1, 3, maybe 6, 5, 4, and then 2, and etc. So there's many ways to write down a cycle. A permutation is a collection of cycles, and there's usual convention is to start each cycle. Each cycle starts with the largest element. So maybe I should switch 1 and 3 here, 3 and 1. Then this is some sort of canonical form. And you can also sort the cycles by maybe decreasing of the largest element. Anyways, this is all not really important. And let me mention another unimportant thing, which is that if I just write 1, 3 is, or any cycle, let's say I write any cycle, A1, A2, all the way up to AK, then if I just write an object like that, then I consider it as a permutation. Is considered as a permutation, which sends sending A1 to A2 to A3, etc., all the way up to AK to A1, and fixing the rest of bracket n. So in other words, if I have, for example, if I have a permutation 1, 3 as an element of S6, then in two-line notation it is given by 1, 2, 3, 4, 5, 6. I'm going to send 1 to 3, 3 to 1, and then I'm going to fix the rest of the elements. And the reason this is convenient is because with this notation, any W in Sn is actually a product of its cycles. So when I write something like this, is the product of its cycles in any order. So in other words, if each of these cycles is itself a permutation. Like this guy here is just a permutation, is just the identity permutation, which sends I to I for all I. And if I multiply all these permutations together, then I get W. So that's a way to factor W as a product of simple factors. Yeah. Does it make sense, or any questions? Probably many of you have seen this before. No questions. All right. Yeah. So, and a particular class of cycles are going to be sort of basic building blocks are going to be transpositions. So a transposition is a permutation of the form ij for I not equal to j. So it's the permutation that it sends I to j, j to I, and then k to k for k not equal to I and j. So you swap the values of I and j, and that's called a transposition. So in particular, I wonder if somebody can guess. So lemma when is a transposition of I and j even, and when is it odd as a permutation? So transposition ij is an odd permutation if and only if some condition if the difference between them is odd. Let's see, that's actually interesting. Maybe I should try an example. For example, let's say I do transposition 1, 3 in S3. So it sends 1 to 3, 3 to 1, and 2 to 2. No, so let's say that's W. And the number of inversions of W is what? Oh, okay, it's 3. So W is odd. And if I do an example of W 1, 2 in S3, then W is 1, 2, 3, 2, 1, 3. So the number of inversions of W is 1. That's also odd. So it's not quite the difference between I and J. Oh, actually, I'm out of time. Yeah, maybe I should continue. If not, if I'm going to continue next time. And thanks for joining the lecture.